team, and Justin Conrad and Lance Berry are my teammate. And right now, I'm about to give you a presentation on the result of the steady state and unit response lab for the past, 4 weeks? Anyway, let's get to it. Okay, outline. Like I say, we're gonna talk about steady state and step response, and I'm gonna show you the measure data of steady state and step response that we found. And I'm also gonna talk about the outcome of what we found, and after that, we hit the conclusion. Okay, this is just the theory and background. Just the same thing that Silver team just discussed earlier. So we're just gonna have the input motor power.
Look for the computer. The way I'm looking at it.
So it's gonna be running percent. So it just basically as the like when you come in, it's just basically you set up like what you want, how many percent that you want the motor to be running at or operating at, and then from there you just monitor on the lab view, and from there it's gonna spit out the output, which is for us it's gonna be an amp. For you guys, it's gonna be like flow rate and so on. This is the schematic of the entire system. So you have the motor over here, and which is connected right next to it is going to be the generator. And when we kick it, turn it on, and just hear a lot of noise. And from there, it's going to run through all the current control recorder, and the current control driver gathers all the information that you put in, and then it's going to transmit and send and receive data and so on. And then from there, it's going to pick up and get sent to the lab view. And also get to see the light, light up, which is we didn't get to see that many of. All right, this is the steady state operating curve that we found. It's just the example of it. We have the input line, which is just already set. So it's going to be, from there, it just take, like as for me, since I'm running, my range was in, because I'm the middle guy, so my range was between 2 and 3. So it took me quite a while just to get a steady state output. And I literally have to run it over a minute just to find that line, that output line to be steady, and also have to be stay within my output range, which is 2 and 3. For Justin, is 1 and 2, and for Lance is 3 and 4. Anyway, from here, it's just when this line, this output steady state line has been established, and from there it just take the data, and from here to find the average of that line is 1.3 amps, and that's the inserted speed of 0 to 1. And it's run at 50%, which is that's Justin range right there, 1 and 2. This is the table. This is Justin's range right here, as you want to get out, and this is mine, 1, 2, 3, and this is Lance area over here. And it's when you look at the input power that I put in, the range that I put in it, it took me quite a while to figure out that if I actually go above 72%, this number right here will no longer at 0.22, it will jump straight over 3, which is land range. And you're gonna see the graph and you're gonna freak out. This is our graph right now. As you can see, because as from the previous slide, I had to use a 0.5 increment just to stay within that range of 2 and 3. So when we're actually graphing it, all the data that I have was pretty much close to each other. So when you look at from 1 to 2, it's pretty spread out. But when it gets to my area, it's already close up, hugging each other. And then when it gets to Lansing, it just pumps straight up and then start to get linear. This graph of our step response, just another example of it. We do a step up of 20%. So, let's see. Yeah, this one is belong to Justin range because he operates in 1 and 2 amp output, and he's operating his input range. This graph here is showing the gain calculation. From here, I found the delta C. Delta C is the range of the lower output compared to the upper output. Let's just take the difference between those two, and you get the delta C. And delta M is just basically the range of the input, the lower input to the upper input. And then from there, it just set up the equation, just delta C over delta N helps get your gain. Okay, for this particular graph, you get a 0.43 amps out of it. Delta tap calculation, we found is at 0.11 second. And the next one should be a time constant. And it's at 0.43 seconds for this particular graph. And this is all the data on the step response of my entire group. And you can see it's just pretty much close, and the dead time is pretty much the same. And in conclusion, to look at the graph, you can tell it's not linear, because I think it's due to my part. I think that's the only reason why, because my input data are pretty much close to each other. So that's why it's kind of clustered up the entire graph. And we'll try pretty hard, like for my part, I try really hard trying to keep the output range to stay within 2 and 3 amps. And for the step response, we use FIT2 to calculate our data. So that's it.